Good morning, champs. Let's understand reaction enthalpy today. So first we need to understand what the standard enthalpy of formation delta HF is. So what you see here is 1 mole of carbon dioxide. So to determine the standard enthalpy of formation for 1 mole of carbon dioxide, we would need to take a closer look into the elements of the substances in their stable form, which in this case is O2 and C. So the standard enthalpy of formation would tell us how much enthalpy is being needed or released for the formation of 1 mole of carbon dioxide. So the standard enthalpy of formation is something which is determined at the standard condition, which is 25 degrees Celsius and around 1 bar. So in this case we would have a heat release, meaning that delta HF is negative or below 0, and we would consider it exothermic. However, if we would need enthalpy for the formation of a mole, meaning that delta HF would be larger than 0 or positive, it would be considered endothermic. So in this task, we are being asked to determine the reaction enthalpy for the following reaction under standard conditions, where we have methane plus 2 oxygens reacting to carbon dioxide and water. The task gives us also the data of the formation enthalpy of each of the substances. So before we start solving this exercise, let me just quickly explain you how to calculate the reaction enthalpy. So the reaction enthalpy, denominated as delta HR, is going to be equal to the sum of all of the species I of the stoichiometric coefficient of the species I times the standard enthalpy of formation delta HF of the corresponding species I. So for the reaction we have given by the task, this would mean that delta HR is equal to the stoichiometric coefficient of the species methane times the enthalpy of formation of methane plus the stoichiometric coefficient of oxygen times the standard enthalpy of formation of oxygen plus the stoichiometric coefficient of carbon dioxide times the standard enthalpy of formation of carbon dioxide plus the stoichiometric coefficient of water times the standard enthalpy of formation of water. So this part represents our reactants, which are on the left side of the equation, and this part represents our products, which are on the right side of the equation. So the stoichiometric coefficient of the products are positive, and the stoichiometric coefficient of reactants are negative. So the stoichiometric coefficient of methane, because it's a reactant, is equal to -1, and the stoichiometric coefficient of oxygen is going to be equal to -2. So for the stoichiometric coefficients, we just have to look into our chemical equation. So we have 1 methane and the 2 of oxygen comes from 2 before the O2. And the stoichiometric coefficient of our product, which is carbon dioxide, is going to be equal. So if we take a closer look into the reaction, we only have 1 CO2, hence +1. For the stoichiometric coefficient of water, if we look into the reaction, we have 1 water only, and because it's a product, it's going to be +1. Again, on this side of the reaction, we have our product, and on the left side of our reaction, we have our reactant. So just let me rearrange the information of this page. Here we go. So we now have all of the necessary information to determine the reaction enthalpy. So let's just insert the values into our formula. So the reaction enthalpy will result in -559 kilojoules per mole. So the negative sign is basically telling us that we have an exothermic reaction. If we would have had a positive value here, then it would have been considered an endothermic reaction. So in the following task, we are being asked to determine the heat release or heat required for the following situation. We have 2 mole of methane and 4 moles of O2 entering at a temperature of 25 degrees Celsius, well, not specified here, but let's say at 1 bar. We have our chemical reaction. We just have looked before, and leaving our system, we have 2 moles of carbon dioxide and 2 moles of water at 25 degrees Celsius. So there is no difference in temperature in this process. So the heat release or heat required, delta H, is going to be equal to the extent of the reaction times the reaction enthalpy. So this we can say for stoichiometric reaction. In one way to see if it's a stoichiometric reaction or not is with the extent of reaction. So the extent of reaction is the molar amount of the species I leaving our system minus the molar amount of the species I entering our system divided the stoichiometric coefficient of the species I. And for a stoichiometric reaction, the extent of the reaction is going to be independent of the species I's you choose to use it with. So what I mean by this is, if we take a closer look of the extent of reaction, in this case, if we take a closer look into methane, so the molar amount of methane leaving our system minus molar amount of methane entering our system divided the stoichiometric coefficient of methane should be equal to the molar amount of O2 leaving the system minus NO2 entering our system divided the stoichiometric coefficient of O2 should be equal to the molar amount of carbon dioxide leaving our system minus the molar amount of carbon dioxide entering our system divided to the stoichiometric coefficient of carbon dioxide should be equal to the molar amount of water leaving our system minus the molar amount of water entering our system divided the stoichiometric coefficient of water. So if we enter the values, so we have no methane leaving our system, hence 0 mole, minus the 2 moles of methane entering our system divided the stoichiometric coefficient of methane, because it's a reactant and we only have one, it's -1, should be equal to the molar amount of O2 leaving our system, which is 0, minus the molar amount of O2 entering our system, which is 4 mole, divided its stoichiometric coefficient, which is -2, should be equal. So we have 2 moles of carbon dioxide leaving our system, but we have no carbon dioxide entering our system, hence 0 mole, divided the stoichiometric coefficient, and because it's a product, it's going to be positive, and because we have only one CO2 in our reaction, which is +1, and this should be equal to the molar amount of water leaving our system, which is 2 moles, minus the molar amount of water entering our system, which is 0 mole, divided the stoichiometric coefficient, which is +1. And for all of these values, the result is going to be 2 moles. And because it's exactly the same for every species I, we can say that we have a stoichiometric reaction in this case. And because it's a stoichiometric reaction, we can use this formula to determine the heat release or required. So delta H is going to be equal to 2 moles, which is the extent of the reaction, times the reaction enthalpy, which we calculated in the previous task. It's going to be equal to -1118 kilojoules. So in this task, we are being asked to determine the heat release or heat required for the following process. So this is very similar to the process we discussed before. However, the major difference lies here that we have a temperature increase from 25 degrees Celsius to 90 degrees Celsius. So one way we can break down the process is as following. So we have our entering molar amount, which is 2 moles of CH4 and 4 mole of O2 at the temperature 25 degrees Celsius. And in the previous task, we have calculated the heat release, which was the extent of the reaction times the reaction enthalpy at the standard conditions. So this we have calculated before, and here we have no temperature increase, so here we would have 25 degrees Celsius for the reaction. So here we would have our exiting molar amounts, 2 moles of CO2 and 2 moles of H2O. So what we can say now, after conducting the reaction, we will heat the products to 90 degrees Celsius. So from the heat release of the reaction, we will use some of its energy, delta Q, to heat up the products to 90 degrees. So we have the same amount of the products, but just heated up to 90 degrees. So the total heat release for the reaction and increase of the process to 90 degrees Celsius is going to be equal the heat released to the reaction plus the heat required to increase the temperature of the system. So delta H we have calculated in the previous task. Now we will take a closer look in calculating delta Q. So delta Q is going to be equal to the difference of temperature times the sum of the specific heat capacity of the species I times the molar amount of the species I. So delta Q is going to be used for heating up our products, hence delta T times Cp of O2 times NO2 times Cp of H2O times NH2O. So delta Q is going to be equal to 90 minus 25 Kelvin times 37.14 joule divided mole Kelvin times 2 mole plus 33.58 joule per mole Kelvin times 2 moles. So delta Q is going to be around 9,200 joules, which is 9.2 kilojoules. Which means that delta H for 90 degrees Celsius is going to be equal to delta H, which we calculated in the previous task, which is negative 1118 kilojoules plus 9.2 kilojoules, which will result in around negative 1108.8 kilojoules. So the absolute value is less than the previous task, and this makes sense because part of the energy is being drained for heating up the products.